Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Ashish Darbari of Axiomise. We're going to talk today about scenario coverage in formal verification. Ashish, what is scenario coverage? How does it differ from what we've been dealing with in the past?
Hi, Ed. Yeah, great question. So, formal guys want to tell you that we can do exhaustive proofs. And what exhaustive means is it's a proof on all possible stimulus, all possible combinations checked. But the problem is nobody sees anything inside a proof. So there's nothing for anyone to visualize. And if your manager or senior tech lead came in and asked you, what exactly did you prove? Yeah, so I kind of did this, and those are usually the reactions that formal verification engineers give to their managers, and it can be a little unsettling. So I've been a long, passionate believer of providing evidence-based sign-off. This particular solution that I've designed is to address this problem of being able to go beyond the layer of exhaustive proofs and be able to provide visual evidence on specific scenarios that could be of interest. For example, typically the manager would say, did you test this? An architect would say, did you check this particular combination? And if you don't have scenario coverage, then you tend to think, I think I did, but did I have the constraint too tight? And it's in the land of guesses, and nobody really likes a guess, not with formal anyways.
Well, let's take a closer look.
Sure.
Ashish, what are we looking at?
Right. So I think before we dive into the scenario coverage, it's important to understand what the coverage solution needs to be for formal verification. So I think we need to understand this problem as a quantitative and a qualitative problem. So we need to be able to describe, for example, if this was in the context of RISC-V, we want to be able to describe the coverage targets, which is basically a qualitative description. We want to be able to then understand whether the formalization of these coverage targets as assertions and covers actually in a metric-oriented way could be measured whether or not something is a pass or a fail. So that would be assertion coverage. We also would like to understand that the checkers are complete, that they don't actually have any holes, and that they are verifying what needs to be verified. And that problem is closely linked to the over-constraint analysis, which is again both qualitative dimensions. But as well as you are doing all of these things, you also need to understand that all of the modern formal verification tools have things like stimuli coverage. Is also stimuli reachable? Are the checkers exercising all of the design lines in the implementation? Are we able to mutate automatically some design lines so we can measure the impact on the properties? So a lot of these features are built in the tools which we can exercise, but none of these five things actually answer the question that scenario coverage is trying to answer, is which scenarios were verified informal, were specific scenarios verified or not. And although we built this industry's first end-to-end vendor-neutral formal verification solution for RISC-V, unless we bring in the dimension of scenario coverage in it, I believe largely the coverage problem is still incomplete.
One of the drivers here is that you're dealing with so much complexity. These chips are just getting more complicated. There's more going on. So really what you're dealing with here is lots of different things and possible permutations, right?
Yes, that's right. That's right, Ed. And it's a very valid point, and that's exactly why we need something like this. So although in the context of an architectural processor verification case, this problem is solving the case of instruction interleaving and operands being exercised properly. In a more complex SOC setting, we need to be able to break down the space of behaviors into meaningful scenarios. And actually, in simulation-based verification with UVM, people are trying to solve that problem with functional coverage. So functional coverage is a technique that is actually addressing stimulus incompleteness, but with respect to certain scenarios. And in some companies, they call it feature coverage. So you can look at this as being similar in the spirit that we are trying to actually answer the question which scenarios are actually reachable or possible or have been proven. What it doesn't tell you is the space of these infinite scenarios, right? So we're not able to dream up all of the possible scenarios. So somebody has to write these scenarios. But how exactly we write it, do we want the verification engineer to express it using complex UVM or SV sequences, or can we find an easily expressible format where users can express their intent and all of the backend work of formalization and running can be taken off the user? So we are focusing on making things simpler so users can express their intent. But what we can't yet solve is whether we have covered this infinite space of all of the sequences from this point of view. As formal verification engineers, the proofs that we do cover all of the possible infinite combinations, theoretically infinite. But this exercise is more trying to solve the reverse problem of being able to verbalize all of the scenarios so that you can see which ones have been certainly verified.
One of the challenges of formal has always been that you have to manually write all these assertions, right? I mean, this is just, it gets more and more complicated as the chips get more complicated.
Yeah, absolutely. You have nailed it. Yeah, one of the challenges is to be able to discover how many to write and identify more richer scenarios. The problem is even harder. So what's happening here is that this thermometer is telling you which things are easier for human beings to do and which ones are hard. And you can notice that being able to describe some of the targets and is not the most difficult thing. Being able to run a formal tool on assertions is not hard. And actually, for cases like processors and other IPs, when you're trying to write an architectural check, you can say, can I check if the AND instruction work correctly? Does the load work correctly all of the time with arbitrary many firings? Those things are not too hard. There is a method to write these things. You can write them, run them. You can then use the mutation coverage in the tools to get the understanding whether the test benches are working correctly or not. The problem is, as you go from the easy bits to the hard bits, and you start describing these scenarios, this is where it gets harder. Because remember, the problem we're trying to solve is not that all proofs have been verified, so trust me, but actually which sequences have been tested. And to be able to have to write thousands of sequences manually to be able to capture the complexity of the intent expressed in English language is not an easy thing. And whether you think of automating this through LLMs or through some other hack is a separate matter.
So how do you deal with this? I mean, you've got all this complexity. What do you actually do about it?
So what we're providing is a very easy to express interface, like an Excel spreadsheet or a CSV format, where you can actually express your intent and just push the button in our tool and let the tool take over from that point onwards. It will synthesize all of these requirements for you automatically. It will prove them in the tool, and you can get a nice dashboard to tell you which of these sequences are possible or not possible. And that's how easy the whole thing is. What are we talking about in terms of accomplishing is the focus on scenarios, but I must mention that every formal verification task that is carried out by us or anybody should actually look at these things. So for example, in the context of RISC-V, properties that we are writing have to be reviewed against the published ISA and the SAIL model. If this was a project we are carrying out on a complex IP for a customer, we would be looking at their microarchitecture specification documents. We'll have to check the pass and the fail. We'll have to review the test bench code. So all of this is still going to happen. It's not like the scenario coverage is a panacea and will take away the onus from you. So all of these things are standard things that people do as formal verification engineers. But when it comes to being able to express all these scenarios, in the context of RISC-V, we have Formalisa. In the context of non-RISC-V designs, this could easily be automated through a solution similar to Formalisa. And that's what I want to emphasize, is not for people to think that this is actually going to take away all of the other concerns about coverage.
One of the challenges here is that what you verify today may not be what you're working with maybe a year or two down the road. Software gets updated, hardware ages. You've got all sorts of different things that are going on in terms of workloads that you hadn't planned for. Can you capture some of that ahead of time?
Excellent. I'm glad you brought it up, because this is exactly where scenario coverage will be so useful, because you don't have to rewrite your entire test bench. For example, you could just literally add a new set of instructions. And what you won't want to do is to check whether they work correctly all of the time, but you may want to answer whether the interaction of some of them is good or not, whether it is what you want from a functionality point of view, from a power point of view, or performance. And those kind of quick to-do evaluations in a formal setting are much more rewarding than to do this with the simulation apparatus. And that's exactly where this kind of a technique would become really handy.
How does this actually work in the real world?
Let me show you an example, Ed. So we built this as part of our Formalisa app for RISC-V, but what exactly is going on is you have the RISC-V ISA, which is an architectural spec, and that has been used to actually build our formal kit, which is the core of all the formal assertions, and that goes through a configuration step that actually adapts these architectural properties to the microarchitecture implementation through a set of phase. Then presumably you have a design, a processor implementation that can then be fed into a formal tool along with our properties, and you either get bugs or you get proofs, and you can use any formal verification tool from any vendor. That is the general spirit of formal verification. This does not address the scenario coverage yet. So what we're going to do in a scenario coverage is to be able to answer this kind of a question. How do we know that all instruction sequence interleavings have been verified? Show me that you've tested all sequences. Prove it that you've tested all sequences. And of course, we can't actually generate all of the sequences because that would be, enumerating the billions of combinations. But we say to the designer or the architect, tell me which ones you are interested. So they could say, okay, I'll give you the scenarios. But what I want to say right now is that this approach is relevant not just for verification, but also for designers and architects. They could use this without having to write a test case or a manual checker or any verification code. It's important to emphasize that this is codeless completely. All you have to write is express an intent, and then everything else just happens out of the box. So we would generate exhaustive proofs that each instruction in the ISA would work always as expected, that scenarios that you've specified in the coverage specification can always happen. So it's important to understand that we're talking about this always true behavior rather than can happen. And you will be able to visualize, you'll be able to see specific waveforms.
What you're trying to do here is bound the problem in a way that makes sense for whatever you're trying to do, because obviously everything is infinite. You're never going to know all the possible scenarios, but you've narrowed it down to what are the important scenarios, right?
Correct. And that happens because either we have the domain knowledge to be able to ask those interesting questions, or we go back to the architects and designers and say, could you give us a space of interesting scenarios that you'd be interested? Because as you said, we can't actually enumerate all the infinite sequences. So we do rely on a close collaboration between the design teams and verification teams at this point.
So drilling down into this, what actually happens on the coding here?
Sure. So let's take an example. Conventional verification relies heavily on architectural testing through simulation. And we're asking questions like interleaved instructions work as expected. So for example, we may be interested in asking, will this sub-instruction followed by an add instruction on this specific register operand combination works correctly? And in a test-based approach, people write all kinds of combinations of tests and operand values, but this is obviously infeasible. So the formal guys come along and we write properties that prove all of the operands and all of the instruction firings. But the architect may want to know, for example, is data forwarding working correctly for this particular combination of instruction, with this particular operand map? And if this question was asked of us, we could very quickly model this in a format that can then be processed to give an answer in a quick turnaround time. That's what is going on here.
How different is this from simulation-based coverage?
Yes, in simulation-based coverage, you would be testing these specific scenarios under a human-driven stimulus. And once you get one instance of it, you will stop, or you could say, I can create more bins and I need more instances of it. In the formal setup, we would give you an infinite number of combinations of the same scenario being tested. And we'll be able to not just tell you that it works once, but we'll also be able to tell you that it works all the time. So infinite combinations of operands and infinite combinations of all of the instruction sequences. Now, when I say infinite, what I mean is the combination is defined, but it will be repeated many different times with different operands. And under all of these combinations, the testing has to come out with a proof. And that is a critical difference between simulation and formal here.
So how do you actually work with this? How does this get implemented in the real world?
Sure. So let me give you an idea from a graph point of view. So remember, these were the proof gate checkers and covers. These are these exhaustive properties, properties that yield these exhaustive proofs, and we can say that the processor has been verified against the RISC-V ISA spec. And the setup has sent the design into the tool, and we could have come back with a bug or a proof. But now we're going to actually augment the flow by adding a coverage analyzer spec, which actually is going to be then turned into this machine code that is scripted by us. And actually, it takes the human readable spec and turns it into system verilog assertions and covers under the hood. And the outcome of this is going to be either waveforms and or reports. So you can then see in the tool dashboard what has or hasn't been proven. There's an entire chain of traceability that is built. So every row in the Excel spreadsheet that you write is mapped into a sequence of properties. So you could go back and analyze them. So if something was to not work, you would find out. If you were curious to probe deeper and visualize some of these, you can do that.
So I've drilled into some of the details, but how does this work under the hood? I mean, when you're dealing with all this stuff, you've got a lot of pieces in motion here.
Yes, right. So let me actually give you more examples. So imagine a spec that looks like this. So this is what typically the spec would look like. And this spec would be then synthesized automatically to then either give you a proof dashboard or a waveform. So let's dig in a little bit more into what these specs look like. So let's look at this particular entry. This says that the instruction that I'm interested in observing, the question that has been asked of me is, does the OR instruction work correctly if it was preceded by a subtraction instruction followed by an AND instruction? And it is the case that the subtraction instruction was issued 4 cycles after reset was detected and was in the pipe 2 times. It could be consecutive or it could be non-consecutive. We are not even expressing it. The tool automatically now makes the analysis. And it was 1 cycle after this was subtraction was issued twice. The OR instruction was issued in the pipe. And 1 cycle later, an AND instruction was sent in the pipe. And now show me that the OR instruction works correctly all of the time under this specific disturbance. So now we are trying to look at a very specific behavior rather than, okay, all firings of OR instructions have been verified arbitrarily many times on all the operands with infinite possible interleavings. All of this is something we already do in the first generation work of the Formalisa without coverage. But now we are able to show you that actually we are looking at specifics as well. So if you were to actually put this thing in a spreadsheet, what comes out of it is all of the backend analysis that proves that OR always work correctly and it can work at all. So at all meaning I'm going to give you some visual evidence, but at all times it works correctly means I'm going to give you a proof that all firings of this combination work correctly. Actually, what's happening under the hood is very beautiful. So whereas the user has only specified something in a format like this, under the hood, what's happening is this. So remember we said for 4 cycles, I don't really care what has happened. The subtraction instruction only ever gets issued after 4 cycles. Now, in these 4 clock cycles, what's happening in the formal verification environment is that any instruction can be here. So actually, although I was only looking to answer the question about a specific subtraction instruction, creating a disturbance for OR to break it, but actually all possible permutations of all possible instructions that are allowed to execute in a design could be here in these 4 cycles. So many more permutations have actually gone in Then the subtraction instruction comes along. Then the OR instruction, which is the observed instruction, we call it OBS. And this is the prefix that is disturbing or likely to disturb the behavior of the observed instruction, followed by a suffix. And not only just this behavior, actually, we also allow sub to be non-consecutive. So now even more instructions could come in. So if any of these instructions have dependencies on the previous occurrence of an instruction, that can actually have an impact. But
So putting this in perspective, what you've really done is you've taken an increasingly complex problem and you continue to abstract it in a way that makes sense because you've bounded the problem, but only the pieces of the problem that really matter to you, right?
absolutely, absolutely. I think this would be an amazing way to summarize it. That actually the space was infinite. We did the formal proofs, and now the space is infinite. Which ones were of interest? So basically, we break it down and come from the infinite space to a more specific space of specific scenarios. So yeah, there's a lot of abstraction going back and forth, um, and I think that's correct. Yeah.
Ashish Darbari, thanks for a really interesting discussion.
Thank you very much, Ed. Thank you.